In this example, let's look at how we can use linear approximation on the square root function to help us approximate the square root of 1.25. The graph of the square root function is in blue, and the graph of the tangent line when x is equal to 1 is in green. And I purposely chose to look at this when x is equal to 1 because 1 is very close to 1.25. That means that the graph of the tangent line itself is going to be a very good approximation for the actual curve at 1.25 because it's almost impossible to distinguish between the graph of the tangent line and the graph of the curve at that point. To do this, of course, we're going to need the equation for the tangent line. To do that, we're going to need two things. We're going to need a point on the tangent line, and we're going to need the slope of the tangent line. To get the slope, we're going to have to find the derivative. Let's rewrite the function square root of x as x to the 1/2 and then use the power rule to find the derivative. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. And if we make that negative exponent a positive, the new expression is 1/2 times the square root of x. Now we need the slope when x equals 1. So evaluate the derivative when x is 1. That gives us 1/2. Now we can use the point at the point of tangency and the slope to write the equation of the tangent line. Substitute 1 for x sub 1, 1 for y sub 1, and 1/2 for m. Distribute on the right to simplify, and then add 1 to isolate y. And that gives us 1/2 x plus 1/2. That is the equation of the tangent line when x is equal to 1. This equation is going to be a very good approximation at any x value close to x equals 1 for the square root function. We want to know the square root of 1.25, so we can plug in 1.25 for x into this linear equation, and it's going to give us an estimate that'll be very, very close to the actual value of the square root of x. Evaluating the linear approximation at 1.25 gives us 1.125. Now, because this is an approximation, a couple of questions arise. What's the margin of error in our estimation? Did we overestimate the actual square root of 1.25 or did we underestimate it? And what do the answers to these questions tell us about the concavity of our graph? Here I've zoomed into where x is equal to 1.25. You can see that the blue graph still represents the graph of the square root function, and the green line represents our linear approximation. Because the linear approximation graph is above the actual graph, we've overestimated. If the linear approximation graph was below the actual graph, we will have underestimated. To find the margin of error, we just take our estimated value and subtract from that the actual value. So that would be 1.125 minus 1.118, and that gives us 0.006966. Because this number is positive, we know that we've overestimated. If this number is negative, we know that we underestimated. So what does this overestimation or underestimation tell us about the concavity of our graph at this particular point? Well, if we overestimated, we know that the graph of our linear approximation is above the original function. And that means that the original function is concave down at this point. If we had an underestimate, which we didn't in this case, but if we did have an underestimate, we know that the graph of our linear approximation is below the graph of the actual function at that point, and that tells us that the graph is concave up at that point. So if we overestimate, we know the graph is concave down, and if we have an underestimate, we know the graph is concave up.